Hello everyone. In this video, I'm going to talk about the harmonic series. It is this infinite sum, 1 plus 1 over 2 plus 1/3 plus etc. Obviously, as the denominator increases, the value of the corresponding term decreases, which means that the upcoming terms that we are adding are less than the previous terms. For example, 1/3 is less than 1/2, and 1/4 is less than 1/3, and so on. And at some point, the denominator becomes very large, so it might seem that the sum of this series is a finite number. But the fact is that this series is divergent, and I'm going to prove this. Let us first see the following definition. Consider a series AN and define Sn as the sequence of the partial sums of this series AN. Let us first see what this means. We know that the series AN is defined as A1 plus A2 plus A3 plus etc. plus AN plus etc. So we are adding infinite terms. Now if we add a finite number of terms in this series, we call this a partial sum. For example, S1 is A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3, and so on. Thus, in general, Sn is equal to A1 up to An, which is defined as the sum of all AKs where k starts from 1 up to n. Now, if we list all the terms S1, S2, S3, Sn, etc., we've got a sequence. And this sequence is called the sequence of partial sums, denoted like this. And of course, n is a positive integer greater or equal to 1. All right. We come back to our definition. If the sequence Sn happens to be convergent, which means the limit of Sn exists and it's a real number, then the series An is also convergent and it converges to S. And by the way, this is called the partial sum convergence test. So if it happens that the limit of Sn does not exist, then we say that An is divergent, and that's exactly what I'm gonna do here with the harmonic series. We start with defining the partial sum, which looks like this. Let's find S1, and it's 1 over 1, which is equal to 1. What about S2? It's 1 plus half. In this proof, I'm only going to find the sums whose indices are exponents of 2. I mean S2 to the power of 0, which is S1, S2 to the power of 1, which is S2, S2 to the power of 2, which is S4, and so on. Alright, so this is S4. Now here I'm going to do a little change. We know that 1/3 is greater than 1/4. Which means if we replace 1/3 by 1/4, we will obtain a smaller sum. Thus, S4 is greater than this, and I repeat, we replaced 1/3 by 1/4, so S4, which is this sum, is greater than 1 plus half plus 1 over 4 plus 1 over 4. Now what is half plus 1/4 plus 1/4? That's 1. So S4 is greater than 1 plus 1, which is 2, but I'm going to write it as 1 plus 2 over 2. Why did I write it like that? You will see in a minute. Let us now find S2 cubed, which is S8. 1/3 is again greater than 1/4. And each of 1 over 5, 1 over 6, and 1 over 7 is greater than 1 over 8. Thus, S8 becomes greater than the sum. Now these two terms sum up to 1/2, as well as these 4 terms, they also sum up to 1/2. So S8 becomes greater than 1 plus 3 over 2. Now here, you might be able to see the pattern. There is some relation going on between the index of the sum and what we get eventually. Let's do one more. S16 is the sum of these terms. Again, 1/3 is greater than 1/4, as well as these terms, they are greater than 1 over 8. And each of these terms is greater than 1 over 16. Again, these two terms sum up to half, as well as these 4 terms and all these 8 terms. So we get 1 and 4/2, and S4 becomes greater than 1 plus 4 over 2. Now let us see what we got so far. S1 is equal to 1, S2 is equal to 1 plus half. Starting from S4, we're getting a greater sign, and this index 2 is 2 to the power of 1, this is 2 to the power of 2, and so on. 1 matches with this one, 2 with this 2, and so on. And this is the pattern. So now we can say that S2 to the power of 5, which is S32, is greater than 1 plus 5 over 2, and so on. Which means we now can generalize this relation So S2 to the n is greater than 1 plus n over 2 for all positive integers n greater or equal to 1. Now if we find the limit of this as n goes to infinity, it is obviously infinity. So this sequence of partial sums, S2 to the n, is greater than another sequence which is divergent. So we can say that this sequence S2 to the power of n is also divergent. And let us remember, we did not consider all the partial sums of the harmonic series. We only formed the sequence of partial sums whose terms are S1, S2, S4, S8, etc. Even though it happens that this sequence is divergent. Therefore, the harmonic series is divergent by applying the partial sum convergence test. I hope you found this video useful. Thanks for watching and see you soon.